Well, let's use our 10 rows to compute the determinant of some generic 2x2 matrix. The matrix is ABCD, and the determinant of it, well, let's use now the rules. The first step is to notice that A and B, well, are essentially A plus 0 and B plus 0. Well, adding 0 changes nothing. But remember that the determinant is row-wise linear, so I can use that rule. And the rule, well, let's split the thing. So I get A0 CD and 0B CD. Again, row-wise linear, just the property. So during this step, I use the property tree here to introduce zeros on the first row. You can see A0 and then 0B, one at a time. Now let's try to do something similar for the row, the second row. So we have C and D, but recognize that C and D are essentially C plus 0 and D plus 0. So I can write this determinant as this one. Nothing changes because these are just zeros. And this is equal to this determinant as well. Now, again, use the linearity on the rows to split this matrix into two matrices. So the 0 stay the same here and here, the A stays the same, A and A. But downstairs, I have 0 and D, and the other is C and 0 here. Use the linearity on the rows. And for the second, I also use like this. You see the idea? Same thing. Finally, I see a column of zeros, but that means that this determinant is 0. Remember, I'm using the 10th rule. The 10th rule says that the determinant of A transpose is equal to the determinant of A. Well, I have here a column of 0. If I transpose it, I get a row of zeros, and I have a rule that tells me that a row of zeros means the determinant is 0. So likewise, the determinant of a matrix with one column of zeros is 0 again. So this is 0 and this is 0. And only this determinant and that survives. The determinant of the first, you use again row-wise linearity to pull A and D. So I get A, D. Here I flip the two rows. I get the first row as C0 and the second row B, 0B. I pull the B, I pull the C, and I get a minus sign because I flip the rows. Minus BC. So you just use the rules, but strategically, because we want to use the rules exactly to introduce those zeros, so that I get a simplified determinants to compute. So I'm like trying to break the original problem into simpler problems. Can you see? By using these manipulations. Very important ideas, because if you look closely, it looks as if I pick the A here, I put 0 here and 0 here, it survives the D, and then I pick the B, I put a 0 here, I put a 0 there, and so only the C survives that. So if I choose A, I have to kill essentially all the other entries on the first row and all the entries on the first column. If I choose the B, I have to do again for all the other entries on the first row have to be zeros. And on the second column, all the entries must be zeros except the one that I chose, the B. Only the C survives here. Can you see the idea? This is very important because it seems like this rule of choosing something on the first row and eliminating everything else on the corresponding row and column is a very efficient way of thinking and using in those rows that we see, the 10 rows that we've seen. And okay, it's like an emergent rule. It emerges from these 10 rows to do this. And let's see in this idea in action when we deal with a determinant of a 3x3 matrix. Now let's compute the determinant of a 3x3 matrix. And the matrix is the one that you see here. Generic, all the entries are generic. And I highlighted the entries on the first row. So let's pick the first entry. And remember the rule that we seen in the previous video about the 2x2 matrix. If I choose the first entry or the first row, I have to eliminate the other entries on the first row and the first column. And this is what you see here, 0, 0, and 0, 0. Then I choose the second entry here. I choose the second entry. And I put zeros on the first row on the other entries, here and here, and also on the corresponding column, here and here. And finally, I pick the last entry on the first row and put zeros here and here and here and here, like you see on this position. So this is the first step of simplifying our original calculation. Now let's look one at a time at these determinants. From this one here, let's now look and focus on the second row. And let's choose now this entry here. The other are zeros, are 0 here. So if I choose this entry, I have to put 0 here and here, just like I did on the first step from here to here. Now I choose this entry, put zeros here, and only 833 survives. If on the other hand I choose this entry, 823, well, I have to put a 0 on 822 and 0, 833 here and here, and only 832 survives. Again, the same thought process of choosing the entries, the non-zero entries. Well, you just repeat the process now for the second one. After doing all these, putting zeros on along the first row and the corresponding columns, now you just focus on the second row. Pick this entry, put zeros here and here, only 833 survives. And finally choose the other 823. Well, you put 831 survives, and 0 and 0, 0 and 0. The corresponding row and column corresponding to what? To the entries to the coordinates of 823. Finally, repeat the same line of reasoning. You get this. Now that you arrive at these simplified determinants, these building blocks of the original thing, it's easy to compute those from the rows. For example, A11, this is diagonal, well, just the product of the diagonal terms. So you get A11, A22 times A33, A11 times A22 times A33. Here is A11 times A32, A23. Remember to flip the rows. Flip the rows to make it diagonal. But if flip, you get to a minus sign here. This minus. Just repeat the same thing. A22, just flip the rows, right? You have to flip one time. So we have A21 here, A212 here, and A33 there. But you have the minus sign, A12, A21, A33. This is what I just said. And finally, for this side, well, you have to flip this time twice. You flip twice, and you get the minus A12, which the minus cancels with that one, and you get A23, A31. Now you just do the same for this case. Just flip as you need to make it diagonal. Use the rule that tells us that the determinant of a diagonal matrix is just a product of the elements of the diagonal, because according to the linearity row-wise, you can also pull the constants. This is what you see here during this process. And finally, the final determinant is just a summation of these plus that. Very simple ideas are involved here. The calculations can be quite tedious, but the idea is simple. Now, if you look closely, there is something very important going on here. Very important. We'll focus on this, and on this, and on this. What you see? What do we see? Well, you see the determinant of this. You see here the determinant of this matrix, right? And finally, you see here the determinant of this. This is very important observation. So it's as if is the first entry times the subdeterminant here. The second entry and the determinant there. So again, remember what I said. You choose the first entry, eliminate the first row and first column, and only this piece here survives. Well, this is the determinant you see here. And again, you just repeat the process. Eliminate the row and column, and only this piece survives. It's a determinant you see here, and so on. Very important observation. Finally, let's try to derive a formula for this determinant. But before going into that, let's just look more carefully at these calculations. We have seen that this piece here, here, and here are essentially the determinant of this submatrix. This is the determinant of this matrix, and this one from that one. But if you look closely, what is this submatrix here, here, and here? Well, this submatrix is the matrix that you get after you suppressing the first row and column. Look at the coordinates. A11 means suppress the first row and first column. So A12 suppress the first one means suppress the first row, and number 2 suppress the second column. And the A13 means suppress the first one, right? Suppress the first row, and 3 suppress the third column. So essentially, the coordinates of these entries that I'm choosing on the first row, these entries, are telling me, the coordinates are telling me which row and column should I suppress. And after I eliminate those rows and columns, I get a submatrix whose determinant I'm computing, and it's important here in the end. Can you see? This piece, and this piece are exactly the determinant of that matrix that I get after suppressing the row and column corresponding to the coordinates of the entry that I pick. Very important. There is, however, something special. There is a sign here. This is plus, this is minus, this is plus. There is a pattern here. I'm going to tell you the pattern, by the way. The pattern looks like this. Plus, minus, plus, minus, plus, minus, and plus, minus, plus, by the way. In other words, let's just give a name to this. The plus sign here, the plus sign that I get here, and the determinant of the submatrix, the minus sign times the determinant of the submatrix, and the plus sign times the determinant of the submatrix. So this sign times the determinant of the submatrix is very important here. It's what we are multiplying the entry that we pick. It's a sign, a special sign, times the subdeterminant. Very important idea. Because that sign times the subdeterminant is so important that we give it a special name. Let's make it a definition. It's downstairs, the definition. It's called the cofactor of that entry. The cofactor of the entry A11 is that sign, so plus or minus, which, by the way, the plus or minus is this piece here, times the determinant of the submatrix. So the matrix, determinant of the matrix with row I and column J suppressed. So essentially, this sign times this thing, the sign times this thing, and the sign times that thing is what you find here, which must be multiplying now the entries that you choose on the first row. And in conclusion, the determinant of A is just look at the first row. So 1 is fixed, is A11, A12, and so on, up to A1n, times the corresponding cofactor, meaning the determinant of the submatrix and the corresponding sign. By the way, notice, I didn't say it, but notice that this row is this, by the way. Can you see? Finally, there is many ways of computing the determinant. This is just the formula. This is the formula for the case on which you pick entries on the first row one at a time and multiply by the corresponding cofactor. But that calculation, you see, that calculation is essentially A1111, A12, A13 times the corresponding cofactor. Can you see? This times that is the dot product. And from the dot product of this with this gives the determinant of A. Similarly, this dotting with that gives me this, the determinant of A, another way. And if you want to choose the entries from the last row, well, there is the corresponding cofactors. Dotting both gives me that. All the other combinations must give us 0. So this formula, this last formula, essentially summarizes all the ways at which row-wise, in which you can compute the determinant of a matrix, all the possibilities.